a little bit of change of direction. So we talked about gradients, Hessians, vector calculus last class. And before we move into talking about general convex functions, we're going to spend today's lecture and Thursday's lecture talking about a very specific, interesting convex problem. And we're going to use some results from convex analysis in the lecture today. We'll prove them next week. But we're going to go in detail through one example that is a very commonly used convex optimization problem that is incredibly valuable. And the nice thing about this particular problem is it kind of brings together a lot of the tools and the ideas that we've been building up for the past 3 weeks. So it's a really nice way to end our kind of first linear algebraic optimization exploration. And then we'll use the kind of machinery we've developed around gradients and Hessians, talk about convexity, convex sets, convex optimization problems. Then we'll talk about the key kind of why is convex, one of the key tools of optimization, which is duality. Of course, before that, we'll talk about gradient descent and descent algorithms, which are particularly useful in the context of convex optimization problems. And then we'll go on to kind of discuss specific examples for the rest of the class after building out a bunch of general theory. So today, again, we're going to talk about this one very specific special example called ridge regression. And to build up to that, we're going to start out by talking about the idea of sensitivity analysis or perturbation analysis. What happens when you might have some kind of noise in your data or in your measurements, and how we can understand how to deal with this. Okay? So I want to use the IPython notebook later, which is why the screen is still down. So just for the first part, I won't be, moving the, be able to move the top. You won't be able to see the top board, but after that, we will do that. Okay? So I want to start with the following problem. Should we start here? No. Let me start with this problem. So we've been dealing with basically ax equal to y type problems for this entire class. Let's consider the specific case where A belongs to R n by n and is invertible. Okay? And we want to ask the following question. Okay? This particular equation represents a set of measurements, basically, right? Every row of this is giving us some measurement. It is giving us some data about what the unknown quantity x is, right? The least squares approach says, well, we want to minimize ax minus y norm squared, okay? What if now we had some small perturbation or some noise introduced into this? So for example, let's say I had my y, and let's say my y was perturbed to y plus delta y, okay? So there's just a small perturbation on this particular y. And because of this, there was a change in x as well. X was also perturbed to, let's say, x plus delta x, right? If our measurements change a little bit, presumably our x will also change a little bit, right? So what we want to understand is, how big is delta x? If a change in, what kind of change in x is induced by a small change in y, okay? And now we're thinking about noise here, or a perturbation, in a slightly different perspective than you might have seen in other lower division classes, right? So when we talk about least squares, for example, in least squares we say, well, we have lots and lots of equations, and the reason we have lots and lots of equations is that they all might be slightly wrong, they might all have some errors or some noises. And therefore, we have a way of basically, by having many, many equations, we can reduce the impact of the noise or the errors, right? Here, we're thinking about this perturbation in a slightly different vein. This might happen due to noise, or it might happen due to a change, but we just want to understand how sensitive is our solution to a perturbation in our measurement, okay? Is the kind of question that we're posing clear? Yeah? Okay. And so the way we're going to think about this is we're going to think about the norm of delta x. Actually, maybe not squared. Let's just think about the norm, the 2 norm. Okay? And we want to think about this in relation to the perturbation delta y, as well as in relation to the perturbation, or as well as in relation to the value of x itself. So if x, for example, is a really giant quantity, maybe a small perturbation isn't a big deal. But if x is pretty small, then we care a lot more about this perturbation. So in particular, what we're going to want to understand is how does this quantity change compared to the norm of x itself. So we're actually looking at this ratio. Okay? And of course, we want to think of this and connect it to, the change in y. Yes?
I have a clarification question.
Yes.
So you wrote y goes to y plus delta y.
Uh-huh.
And the arrow is not on top of delta. So
Oh, sorry. It's this is just my fast writing on the board. So I'm thinking of delta y as a vector.
So delta is like a matrix?
No, delta y is just a notation that I'm using for a perturbation. So I'm thinking of not the best notation. I don't want to think of delta as a, so I want to think of maybe, I should think of it as delta sub y.
Okay.
But I'm just using the notation that's used in the textbook to be consistent. But we could make this all delta sub x's and delta sub y's. Good question. Is this clear to everyone? Like this, basically, x and y are both in Rn. Delta x, delta y are also vectors in Rn. Yeah?
Small change in delta y is a small change in y.
In y, yes. Delta y is a small change in y. Okay, like think about it. If you had some y vector like this was your y vector, and then there's some delta y. So then this is your y plus delta y. Okay? Yes, question?
So in essence, we're thinking how the result, we're looking at a result and we're saying how the result, the changes in the result affect our measurement. Don't we usually go the other way?
No, we're not quite. So the question is, what is the measurement and what is the input? So remember, when we're thinking about ax equal to y, our x is usually our unknown. And y is our measurement. Right? So A is our data matrix. So this A represents basically the experiment that we're doing, right? We're collecting some linear combinations, and we get an output, which are the entries of y. So this is our measurement. Okay, good. So to write this out, so this is the quantity that we want to understand. To write this out now, I want to think about, what is the problem, to pose it more carefully. I have A times x plus delta x is equal to y plus delta y, okay? So I'm saying that there's some perturbation, and I want to understand what this quantity here is. And I want to understand the relationship between the solution of this system of equations to the solution of this system of equations, okay? So I know, how am I defining x? I'm defining x as that x that solves this thing, okay? So since I'm defining x this way, from this, I can basically say that I know ax equal to y. So I can write, therefore, that a times delta x is equal to delta y. Okay? And I want to use this now to learn something about the norm of delta x. So I can therefore, since I'm assuming that a is square and invertible, I can write delta x is equal to a inverse delta y, right? And now, can I use this equation to get some information about the norm of delta x in terms of a and delta y? What have we been talking about that we could use to relate the norm of delta x to the quantities on the right-hand side? Someone? Anyone? Yeah? The matrix norm, right? We've been doing this for a while. So if I think about the 2 norm of delta x, this is equal to the 2 norm of this vector, right? But can we say something about this in terms of the matrix norm of the matrix A inverse? What is the matrix norm? Remember. Recall. What is the 2 norm of a matrix? It's the max of A times some vector, maybe y. Right? Where y is equal to 1, or alternatively, how else could I write this? Divide it by the norm of y, and then this is max over any y. Right? Or not 2 norm here, just y. Right? So now how do I use this here? What can I therefore say about, so what is this saying? This is the 2 norm of A is telling me the maximum scaling for any vector. Right? People look like they're seeing this for the first time. We've seen this before, right? Some interaction, some validation. Yeah, question? You can upper bound the value on the right. Great. So how would you upper bound the value on the right? Wonderful. And what else am I going to need? Is it just this 2 norm? I have this here, right? So what do I need here? The norm of this vector, right? So A is multiplied by some vector, right? The maximum possible norm of this vector is going to be the 2 norm of A times the norm of the vector itself, right? That's the definition of the 2 norm, or the spectral norm. Yes? Good. So this is by definition of spectral norm. Okay, good. So let's call this thing inequality 1 or something. This is 1. Okay, so I'm kind of on my way to being able to bound this quantity. What else do I need to bound, or what else do I need to be able to say something about? Yep. So what can I say about the norm of x? Do I have any equations involving x? I had to bound this quantity now. What's the equation that I have that I'm going to use for this? Someone else? Yeah. Yeah. Go ahead. Yep. Can we do the same thing? So we have ax equal to y. So now what are we going to do? We want to be able to sound, do we want an upper bound or a lower bound on the norm of x? Do we want to say that norm of x is bigger than something, or do we want to say it's smaller than something? What we want to be able to do, we want to say this ratio is this ratio being big a good thing, or is this ratio being small a good thing? Small, right? So so you want to basically be able to say that this thing is less than or equal to something else, right? So we want to have delta x have an upper bound. But what do we want for the norm of x? Do we want an upper bound or a lower bound? A lower bound, right? Because it's in the denominator. Okay? So now, to get this lower bound, what can I do here? Well, I can just write this way. Again, I can use the definition of the 2 norm. This implies that the 2 norm of y, which is equal to the 2 norm of ax, what can I write? This is less than or equal to the 2 norm of a times the 2 norm of x. Right? And does this give me now an upper bound or a lower bound on the norm of x? A lower bound, right? Which is what I want. So I can write that the 2 norm of x is now greater than or equal to the 2 norm of y divided by the 2 norm of a. Why can I divide by the 2 norm of a here? It's a constant, but what is the one constant I'm not allowed to divide by? 0. So why is this a legal move? A is invertible, right? So that means it can't be the 0 matrix. Okay, good. So now, can I take this, can I take 1 and 2 and get a bound? So combining 1 and 2 gives me that delta x what is this less than or equal to? Well, I can take that thing over there, A inverse divided by norm of A, right? Which basically is equal to the norm of A times the 2 norm of A inverse times delta y by y. Okay? So now we have this quantity, right? So I've managed to find a bound that relates the relative change in x to the relative change in y, right? If the change in y is small relative to y itself, then the proportionality of how x will change with respect to x, of how delta x will change with respect to x, is given by this thing, right? This multiplication. But can I say something more about this, or am I stuck in this 2 norm definition, which is kind of ugly? So what is the 2 norm? Is there a simpler understanding of this 2 norm? This is the definition, but what else is the 2 norm? Yes, but there's another thing. Frobenius operator norm, not Frobenius norm. Singular value, right? So what is this? This is equal to sigma max, right? The largest singular value. Great. So can we write this instead as sigma max? Okay. Now, what about this guy? This is the largest singular value of A inverse, right? What do we know about the singular values of A inverse? Is it a question or an answer? Great. Wonderful, right? Singular values of A and A inverse are reciprocals of each other. Therefore, this is going to be 1 over sigma min. Does everyone see that? And remember that A is invertible, so it has no 0 singular values, right? We're assuming this here in this calculation. So we can easily, it's legitimate to take 1 over sigma min. Okay? This means that we can write this. Okay, I'll erase this and just write this as sigma max over sigma min times this delta y by y. This quantity is called the condition number of a matrix. What it's saying is that if your ratio between your largest and your smallest singular values is very large, if this is big, then a small change in your measurement will cause a small sorry, got that wrong. If this is very large, if the condition number is very large, even a small change in your measurement is going to cause a large change in the unknown variable, in the quantity that you're trying to estimate, right? But if your condition number is small, small errors will only have small effects. So the condition number of a matrix captures basically fundamental properties of your measurement, right? And again, similar to the kind of least squares, right? In least squares, whether or not A transpose A was invertible, or whether or not AX equal to B has a unique solution or multiple solutions or infinitely many solutions, depends, only on whether A transpose A is invertible, the least square solution. Similarly here, this is again only properties of A that are defining the condition number, right? They're not being defined by the properties of Y. Does everyone see that? So this quantity is something that we're going to use. In particular, we can think about this in the context of least squares. How is this useful in the context of least squares? So the least square solution that we have for a system of equations is A transpose A times A transpose B, right? But least squares in general thinks about a tall matrix. Yes, question?
Yeah. Does this then become the problem become like, how do we construct A?
The question is, does the problem then become how do we construct it? It's like, so what if you calculated this condition number? So essentially, yes. Basically, if this condition number then tells you, by looking at your A, you can understand if your measurements are going to be very sensitive to some measurement noise or very robust. So if you have an A matrix with a small condition number, And you know you're doing an experiment and some little bit of jitter comes in somewhere, some extra light energy, something seeps in. You can be fairly sure that, okay, you know, my result isn't going to be perturbed that much. But if you've designed an A such that the condition number is large, or nature has given you an A such that the condition number is large, then the result or the solution that you get from solving this equation, which is what you actually get, is not going to be close to the solution of the equation that you actually wanted to solve. Another question?
Seems unlikely that your data matrix is going to be like square.
Seems unlikely that your data matrix is going to be square. That's a wonderful question, because I exactly want to talk about that. So we'll come to that in a minute, but least squares has a nice property that will save us. Yes?
How exactly is the operator norm different from just a normal norm?
So this we've talked about 2 lectures ago. We defined the operator norm and the Frobenius norm. Operator norm tells you how much a matrix scales a vector. So go review the Eckert-Young lectures, and that will help there. It's talking about the matrix as an operator, versus the Frobenius norm is talking about the matrix as a block of data. So it's more like just the normal vector norm. The Frobenius norm is like a normal vector norm. Other questions? Yes? What is a 2 norm of a vector? We defined this in the first lecture, right? Just the 2 norm of a vector is just the sum of the squares of the element's square root. So is there something I'm missing? Okay. Let me come to answering your question about what happens. Like, this is only defined for square matrices. What about non-square matrices? In particular, we're always interested in least squares, and least squares is definitely not a square matrix in general, right? So if I think about, assuming that A transpose A is invertible, if I think about this solution to the least squares problem, I can write the least squares setup in terms of the normal equations. Right? And I can write this as A transpose A times X is equal to A transpose B. Okay? Right? This is the least squares solution. Everyone know that, right? I can just rewrite this way, and now, just this little rewriting, what is the nice thing about this matrix? Square. So instead of thinking about the condition number of A, I can think about the condition number of A transpose A. But the nice thing is that the singular values of A transpose A and the singular values of A are also very nicely related, right? So basically, these are all things that are proportional to each other. And so since the condition number is not something that you're going to use in a calculation, but it's something that you're using in a heuristic way, you're looking at whether it's large or whether it's small, looking at the condition number of A transpose A is just as useful for us. Okay? Does everyone see that? Yes, question?
Is there any relation between the condition number of A and the condition number of A transpose A?
Yes, small homework problem, basically, because what is the relationship between the singular values of A transpose A and A? But you'll do it out. It'll take a few calculations, but yes, good question. Other questions? Everyone with me? Okay, so now let's try to see this actual, let's play with some data, right, and see how this manifests when we're actually dealing with something real. Okay, let me hope I can project this. PCs. Please work. Okay. Not fun. This worked just a while ago. Why won't this work now? It came on, but that was not that was the other thing. That was not the thing that I want. Okay. Okay, can everyone see this? Yeah? Okay, you don't need to be able to read every line of code, but it's important that you kind of understand the high level of what I'm doing. Okay. So for those of you who took 16A with me, you might have seen this particular plot, which is the demo that we did in 16A for trying to fit an ellipse to a set of points, right? So I can use a least square setup to try and fit data to a polynomial. So if I have, for example, some kind of, ax squared plus bx plus c equal to 0, then, and I have data points x, or let me just call this, and I know that I have, let's say, x1, x2, so on and so forth, are points that satisfy this equation. Then I know that I can write my vector of unknowns as ABC, and I can write a data matrix of x1 squared, x1, 1, x2 squared, x2, 1, equal to 0, 0, 0, as a least squares problem, right? And I can use this and use data to basically estimate a polynomial or fit a polynomial, right? Everyone remembers this? So this, for example, is if I wanted to plot an ellipse, but I'm not actually going to talk about that. I just used the same notebook. So here now, let's say I want to fit a cubic polynomial, okay? So I have some data points. Let's say I have 30 points. And I'm looking at them, and here I'm doing it as a demo. So what I'm doing is I'm actually taking the true polynomial. I'm generating a polynomial. This is the polynomial I'm generating. Then I'm adding noise to that polynomial, and I'm plotting it, right, to generate some synthetic data. So the blue points represent the true polynomial, and I'm pretending that all I've received about this polynomial are these red pluses that are the perturbed points. Everyone see that? Is the colors are clear, right? Or the size is okay? Okay, good. So let's say now I have these red points. I can use least squares to basically estimate and find the true polynomial, right? So I do that. I basically, generate this data matrix, and I run least squares, and I can estimate some coefficients. And I can then reconstruct the polynomial on those same data points. And the reconstructed polynomial is these green stars here, okay? And it's not exactly along the true polynomial because, well, I was fitting the red data points, right? So obviously there's going to be some error. And I can have a quantity for my training error, which is my difference to the input data points. And I have my true error, which is my difference between what I predict, where the green point is, and where the blue point really should have been, right? And if I look at my estimated coefficients, so what was my true polynomial? My true polynomial was 1, 7, minus 11, 4. And here I get 1.1, almost 7, minus 10.8, 3.9. Like, this is pretty good, right? If I just want to look at how good I'm doing compared to the coefficients that I actually input. So this is straightforward. You've all seen this before. Nothing fancy, nothing interesting. OK, good. But now, what happens if I were to say, instead of a third-degree polynomial, this I assumed that I knew I was fitting a third-degree polynomial, right? But instead of a third degree polynomial, if I was to fit, let's say, a fifth degree polynomial, well, then I can have some reconstruction. These are the green points are the reconstruction. And I can have some coefficients. So now if the fifth degree polynomial, so I'm going to have now 6 terms, right? 6 coefficients that I'm going to estimate. And a good estimation would actually just put the term for x to the 5 and x to the 4 to be 0 and just estimate the right thing. But because we have noise, we have this phenomenon of overfitting, right? And so now I'm using the fact that I have these extra wiggles. So a fifth degree polynomial will give me 2 extra wiggles compared to a third degree polynomial. So I'm now ending up fitting a little bit of the noise too, right? And so I have some coefficients. They're not necessarily doing better. Like I could, if I was to increase, maybe make this a 10th degree polynomial, I could have even more overfitting essentially. Like my first 4 coefficients, which are the ones I care about, are doing less well than I would have wanted, okay? So I can do this, and I kind of like have this plot here. So what I'm looking at here is the x-axis is the degree of fit. So I'm saying, am I fitting a cubic or a quartic or a fifth degree, sixth degree? And the y-axis is the true error and the training error. So as you can see, that basically I go to degree 3. My training error really drops from degree 2 to degree 3 because suddenly my model has the expressive power to capture what is happening in the data. And then the training error is kind of flat, but it's going down a little bit, right, as I increase more and more. My true error drops, but now it starts increasing as my degree of fit keeps on going up, right? Because I'm now fitting the noise, and I'm learning something. I'm learning the noise instead of learning the true underlying polynomial. Does everyone see this? Okay, good. I see lots of nods. This is great, right? This is like a clean story. We're starting to understand overfitting. We're starting to understand some little bit of impact of noise. But let's do the exact same thing, okay? Except now, instead of looking at the range that I was looking at before, I'm looking at the same polynomial, so this exact same polynomial, but my initial data points, I was looking at between 0 and 2, okay? Instead of looking at values between 0 and 2, let us now look at values between 200 and 202. I've just added a shift. Still 3 points, still adding the exact same variance of noise, nothing different. I do the same thing. I have the points. Now I have the noisy points. It's just that now, because the scale is different, it looks like the red crosses are exactly on the blue dots, but that's just because the noise is such that the visualization cannot capture it. Does everyone see that? But I'm adding a noise here. Does everyone see this? Okay. I do the exact same thing. I do least squares, call least squares right here. I reconstruct the polynomial. And now again, the reconstruction is basically the green stars are exactly on top of the blue dots, so you can't even see the blue dots that are plotted underneath, okay? Okay, good. This is for a third degree. And now I can do this again for higher and higher degrees. But what's happening here? When I look at this exactly fit dead on, I have some training error, and I have some true error. But what are the coefficients that are being estimated? My first term was 1. I am now estimating 2 into 10 to the 6 as my constant term. That seems like a pretty bad mistake, right? Yes, I can fit the data, but it's kind of giving me meaningless stuff, right? And if I was to, here I'm evaluating this true error in this exact same range, but if I was to evaluate how my function is doing in any range other than this 200 to 202, my true error would explode, right? This is clearly not a good thing. But I didn't do anything except add a constant. Linear shifting isn't supposed to change anything, right? In none of our theories so far do we account for this. So what is going on? What is happening when instead of looking at points from 0 to 2, I'm looking at points from 200 to 202. The A matrix that I'm setting up here, right, when I had my x's between 0 to 2, this x1, x2 were all like 0, 2, 4, like x was a squared, there was a cube. 4 cubed was the kind of, 2 cubed was the largest number that was being put in there. Now what is the largest number that's being put in there? 200 cubed, right? So now if I start to think, what do I want to think about of this matrix to understand what might be happening here? The condition number, right? The singular values of this thing. The singular values of this thing are huge. And so the small bits of noise, the little bit of jitter that is being added, like in these red pluses, it's invisible on the plot. But it's causing, right? Otherwise, like we know from the theory of polynomials that, you know, to fit a third degree polynomial, I need 4 points. Exactly, right? Uniquely, 4 points uniquely define a third degree polynomial, right? I have 30, and somehow I'm getting it wrong. Why? Because of the noise. And why? There was noise before too, but I got it pretty good then. Why? The impact of that tiny perturbation is being amplified by the ginormous condition number of this matrix. So what is, like, you know, let's just look at it. So if I now look at the SVD of this, right, I can find the SVD of my A transpose A, and look at this condition number. It's kind of big. Okay? Everyone with me till here? I'll pause and take a question. We good? Thumbs up? Yeah, question at the back. First extreme back and then here.
Oh, those are the aggressive thumbs up. Thank you.
Oh, okay, good.
Can we do like the technique we did in homework and center? That's still kind of interesting answer.
Could we do the technique we did in our data and in our homework and center the data? That's a great question. So centering the data is something that you do often in the context of principal components. But here, because you're looking at, like here, what is this giving me? This is telling me that I have A times 200 cubed plus B times 200 squared plus C times 200 plus D equal to 0. This is the equation that I have, right? There isn't really a clean way of centering this data in the way that you could do it for principal components, because you're not trying to find kind of the dimension, you're not trying to understand anything about the dimensionality of the data itself. Here, where the data point is actually matters in terms of our ability to predict stuff, because there, what you're trying to do in principal components analysis is you're trying to understand something about the underlying structure of the data. Here in least squares, you're trying to understand something about the underlying structure of the data, but also using it to predict going forward. And so there's I can see exactly where you're coming from, but that direct technique does not quite map to the situation here, because there's no way to kind of d-mean this, because there's this constant d, and maintain the structure of the data that you're given. Excellent question. Yes, question?
How do we know when our condition number is going to be the least?
How do we know when the condition number is going to be the least? Excellent question. We won't in general know that the condition number is the least or the max. Like, it's kind of a property of the experiment that you've set up and the data that you have. We will use a condition number more in the general sense of, is it small or is it large? Or is it smaller than something and larger than something? So we use this idea to compare different matrices or their properties as opposed to something in absolute. So we wouldn't typically think of like minimize the condition number, right? Because minimizing the condition number, it's a relative thing. It's talking about how does one matrix amplify the error compared to another. Yeah, good question. Yeah.
So when we have other three
I'm going to pause you here because I think I can see where your question is going. So the question that he's asking is that if instead of looking at A as it is, I can think about A in the context of its SVD and think about, well, maybe let's just think about the dominant directions in A. Let me think about, you know, the principal components of A. You can actually formulate this problem out formally as principal components regression. If I have time at the end of today's lecture or next lecture, I will actually work this example out. And by the end of that lecture, your question should be answered. But it's a complex question, so hold it till next lecture. And I will maybe pause questions here just so that I can get through the rest of the material. Okay? Good. So now what are we going to do? We have bad condition number. We need to make condition number smaller, right? So we have this big A transpose A inverse that is a problem. So what we're going to do is we're going to do what I call this big hack, okay? And if I have something like, basically what's happening, right? What's happening is that I have some singular values that are kind of in this inversion that are getting small, which is causing this large condition number. So if I have something that's very close to 0 and I'm trying to invert it, that's bad. So if I wanted to push it a little bit away from 0, I would just add a constant, right? So what I'm going to do is I'm going to just add a constant, essentially, to my solution to least squares. Instead of solving A transpose A inverse, I'm going to solve A transpose A plus lambda I inverse times A transpose B. Okay? That's what this line of code is doing. And I'm just going to choose lambda completely arbitrarily to be 5. Okay? Now I can find the singular values of this matrix, find the condition number. Still pretty big, but it's much smaller than it was before. Okay? But now let me try to actually fit where is my plot of this fit? Weird. Okay, I seem to have skipped a plot here. But, okay, let me just do this the hacky way. So I define my A here. And okay, give me a minute. I don't want to waste time in lecture figuring this out. I should just basically, the point is that this works. But, I can't believe I didn't plot this. I'm sorry. 1 second. Let me see if I can do this in a hacky, quick way. Okay, yes, this is still not what I want, sorry. Still not what I want. Okay, I will show this to you next class. Point is that by adding this inverse term, this works. And now if I look at basically what I have on this plot here is the degree of the fit and the error, and I can see that my true and my test error are again, being minimized at 3, and you don't have this phenomenon of it increasing later on. So with this additional term, I'm kind of doing better than what I would be doing here. I don't have these horrible singular values, and I can recover reasonable coefficients. I'm sorry I forgot to plot the final solution, or it was there, but I don't know what happened to it. I'm sorry about that. Anyway, I'll show you this next lecture. I don't want to waste time fixing this right now. So I want to now understand, why does this work? Why does adding this random lambda actually help solve the problem? Okay? So the first thing is that we want to look at now, this x is equal to A transpose A plus lambda I inverse A transpose B, instead of and by somehow adding this arbitrary lambda I, where we don't even know, we picked some arbitrary value of lambda, this is somehow giving me a more stable solution than I would have gotten without it. Okay? So the first thing I want to understand, basically, is how is this matrix related to this? And this you've seen before, right? You've seen the shift property of eigenvalues. So if I have some matrix A, and I consider A plus lambda I, what are the eigenvalues of A plus lambda I as compared to the eigenvalues of the original matrix A? How can you see this? Well, let's say that V was some eigenvector of A. What do I get out? This is just AV plus lambda times V. AV, let's say, gives me some corresponding lambda. Let me call this V1, V1, V1. This gives me some lambda 1, V1, which is the eigenvalue of A, plus lambda times V1. So this is lambda 1 plus lambda times V1, which means that if lambda 1 is an eigenvalue of A, lambda 1 plus lambda is an eigenvalue of A plus lambda I. Everyone see that? So basically, by adding this thing, I've just shifted the eigenvalues of this, or the singular values, effectively, right? Because for a symmetric matrix, the eigenvalues and the singular values have a direct square root relationship. Okay? So by adding this, basically, I'm making the smallest eigenvalues bigger, and therefore, hopefully, reducing that condition number, right? Because that has a sigma min in the denominator. By bumping sigma min up, even by a little bit, I can have quite a bit of an impact on the condition number. Everyone see that? Yes, question?
Don't you also increase the biggest?
You will also increase the biggest singular value. But basically, if you have something really tiny, like if you have, let's say, 100 divided by 10 to the minus 6, and you add 1. So if I change this to 101 over 1, 10 to the minus 6, suddenly you've had a huge impact on the condition number, right? Because your smallest singular value might be really tiny. Yes?
How do you find a lambda
Great question. So how do you find the lambda? That is really the question of hyperparameter search. And a class like 189 would talk about this more, but you would use a technique like cross-validation to do this. So here I actually have a plot about how, as you vary lambda, your true and your test error changes. So for example, as lambda, I start at 0, and my true error goes down, 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 and then pops back up. So you can look at this plot and believe me that it works, even though I didn't show you the polynomial. But based on this, you can see basically this is plotting the true error, right? Does everyone see that? So here, ideally, I mean, I would never have access to this plot in a real data situation because I would never know what my true error is. The true error is only something I know in my imagination. But you could compute something like this using cross-validation and look for elbows in the plots to find optimal values for hyperparameters. But hyperparameter search is like a whole other field of its own. That's for 189 to teach you all. Why couldn't we just change some eigenvalues and not others? You could selectively change eigenvalues by adding specific vectors in specific directions. It's just more complicated. And you would then have to know exactly what, you'd have to find the SVD of A, you'd have to find exactly the appropriate basis. So this is a more general way to do this. If you wanted to be very precise, you could just shift some specific eigenvalues. That would be approached, but you might have to be careful about, because you're modifying some directions and not others, about other effects. I imagine that this is actually fairly well studied. I don't know about it off the top of my head, but thinking through it, I'm pretty sure probably someone out there has developed a theory around it. At the back, white t-shirt.
Is there any price that we have to pay, so to speak, for adding this lambda? Like, is there any downside?
Great question. Is there any downside? So yes, there can be a downside. So for example, here what you're seeing is that, for some lambdas, I keep improving. But then as I keep increasing my lambda, like I'm basically perturbing away from the true solution in some sense, right? And so for a bad choice of lambda, I could actually keep increasing my true error. And as we're going to do some analysis, this will become more clear. So you'll see more effects of choosing a bad lambda just in a few minutes. Okay? Last question. Someone who hasn't asked a question yet. You've both asked questions before. Okay. No last question. Okay, you haven't asked a question yet. Yeah, so here, this is because I'm not really doing any kind of cross-validation, because this is a classroom demo. In reality, you would not just look at the training error, but you would actually do cross-validation to find out what your hyperparameter should be. Okay, so with this now, I want to introduce the idea of ridge regression. So here we have some hack. We have just arbitrarily decided to add a lambda I to our solution. And somehow things seem to be getting better, right? We have a plot that says it's getting better. The question is why and what is the mathematics behind this, right? So that's what we need to actually understand now. So now consider this arbitrary optimization problem. That is a modification of least squares. Minimize over x, ax minus b whole squared plus lambda squared x squared. So I've taken my least squares objective and I've added to it a second term. And what is this second term saying, right? I'm trying to minimize over x. This second term is saying, what kind of x's are bad for me? large ones are bad, right? I'm saying I'm choosing a lambda, basically, this is lambda squared, so it implicitly is always 0, but I could also just make this lambda and put lambda greater than 0. It's saying avoid large x's, right? Which was exactly the problem that we were having in our demo, right? But how is this related to that hack? That's what we want to try and solve next. So I have this. This is now a nice quadratic function. We haven't proved this yet, but we know that this is a convex function. Okay? So just assume for now that this is convex, and therefore we can find the minimum, and it will be a unique minimum, by taking the gradient of this expression and setting it to 0, right? That's what we just set up last lecture to do, right? Everyone remember that? Okay. So, trust me that it's convex. Trust me, therefore, that when you find the stationary point, it's going to be a minimum and not a maximum. Like, it looks like this and not like this. So, why don't you actually compute the gradient of this while I do it on the side? So this is f of x. Find the gradient and set it to 0. So this is just equal to ax minus b transpose ax minus b plus lambda squared x transpose x. Expanding terms, this is basically x transpose ax minus x transpose b minus b transpose ax plus lambda squared x transpose x and plus b transpose b. So the gradient of f of x, which we nicely set up in last class to do. Yes?
Quick question. Last class, you actually proved that heap is a minimizer and the gradient is equal to 0.
Yes. Yes, we are using the other exactly. That's what I'm saying. Like, we have not proved that this is valid yet, right? That was the big caveat. We have not proved that this is valid yet. We will prove it next class or next week, but we're using it here anyway. Okay? So we're assuming that by setting the gradient to 0, we're going to find the minimizer. We have not proven this yet. All we know is the other direction, as was pointed out. That big caveat that I announced at the beginning of starting this problem. Okay. This gradient is now 2 A transpose A x minus 2 B transpose A transpose plus 2 lambda squared x, right? So this is the quadratic term, remember? We found the gradient of this last time. So there we just did x transpose ax, and the gradient is A plus A transpose times x. Remember that last time? But this is now A transpose A, and it's equal to its transpose, so you get a 2 here. These two terms are scalars. They're actually equal to each other. So this is just, I can just remove this term and put a 2 here. This is just a vector. Like, so this is some vector transpose x. This is a dot product. We did the gradient of this last time. So this is what you get. Right? And here this is just xx transpose with a lambda squared. So I get just 2 lambda squared x. Yes, question? Because I want this needs to be a column vector for dimensions to match, because like we did last time, if I have gradient of c transpose x, this is equal to c, right? Remember, the gradient is always the same dimension as the original vector. Okay? Everyone see this? This is just taking derivatives. This is just gradients. Like we did every one of these calculations last time in class. Yeah? Okay. Now if I set this to 0, never mind. What do I get when I set this thing to 0? I get A transpose A plus lambda squared times x is equal to A transpose B, right? The x that satisfies this thing equal to 0 is the same as this. Lambda square I, thank you. Yeah? But what is this? What does this mean? What is the solution to this? What is the optimum x? Convenient. Question?
Why do we remove the lambda squared?
Oh, because I write really fast on the board and I make typos.
Also, is there like a geometric solution to like
Is there a geometric solution? What do you mean by is there a geometric solution?
there's like a geometric proof of these squares?
Oh, is there like a vector space interpretation of it? There isn't a nice elegant proof the way we have for least squares, other than replicating the least squares proof with instead of thinking about A, thinking about, but there's not a nice picture of what happens to the matrix itself when you shift its eigenvalues. Yeah, there's not a vector space picture. I mean, it's telling you when you change the eigenvalues of something, you're changing how it interacts with a vector, right? You're not changing anything. It's not easy to visualize it in terms of the column space or something. Nice, like in that case. Yes, question? Sorry. Hey, people, shh, I can't hear.
Like for the lambda that we have in a minimizing function, like aren't we assuming that like x should be like kind of near 0 again? Like why do we make this graph?
Great question. You're saying that by writing this term here, which we call a regularizer, by the way, aren't we assuming that x is kind of close to 0? And the answer is yes. This kind of optimization is saying that we have some side information, maybe about what the value of x itself is. And we're trying to incorporate that into our optimization problem or into our framework. And so it might not be true that x is small, but in many engineering problems, when you're trying to find a solution to something or when you're trying to build something, you actually do want small numbers. And so is there a way of proving that somehow, there is a heuristic element to this, right? Because you're choosing lambda somewhat arbitrarily. Yes, you'll optimize based on your data, but there is a notion in which this is now an interaction with your data. It's not like this is the one provably best thing to do, right? All you can prove is that if you were to consider this solution, this is the quadratic that you're minimizing. Okay? Yes?
Is there supposed to be a plus?
No, there is not supposed to be a plus over there. Good. Yes?
Question. So it seems like ATA is assumed to be invertible to begin with.
Yeah, it's assumed to be invertible to begin with, but might have some small singular values, like not nicely invertible because it has a bad condition number.
Sure. And what is the intuition of randomly choosing a lambda and then plus lambda square I, and then the resulting thing is also invertible? Is it because like ATA is a very large matrix or something?
Well, no, now when I look at the so the question is like, why do we know something about the invertibility of this matrix? But when I'm looking at the invertibility of this matrix, I know that every single eigenvalue for this is lower bounded by lambda squared. So this matrix is guaranteed to be invertible because lambda squared is positive. It's a good question. Okay. So I'm going to do one last thing in 5 minutes that we have. So when we have our equation, ax is equal to b, okay, we can think about this as these equations, right? This is my a, this is my x, this is x1, x2, this is b1, b2, this is, a1 transpose, maybe it's the first row. Each of these is a measurement, and this is telling me something about my x vector, right? Now I'm telling you in the ridge regression context, I want to think about this as like, oh, x is not too large, right? Or x is somehow close to 0. Let's say I had some side information that told me that x is close to 0. What's another way of writing that, right? I could tell you that, well, maybe if I told you somehow x1 is very close to 0 as some side information. Could I incorporate that into this matrix, into this set of linear equations? What if I did the following? What if I added a row here, and I said 1, 0, 0, 0, 0, 0, 0, 0. What does this tell you? This is saying x1 is 0, right? Of course, it's a set of noisy equations, so there's some noise. It's not exactly 0. And what if I added another row that was 0, 1, 0, 0, 0? I'm saying x2 is about 0. Okay? I could do this if I knew that every entry was close to 0. I could add basically an identity matrix here, right? This could be identity. And I could add a column of zeros here, right? What if I was really, 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 really confident that everything was 0? I could tell you that 10 billion times x is also close to 0, right? Or if I was not really that confident, I was like, kind of, maybe it's 0. I could tell you that, like, I don't know, 10 to the minus 6 is close to 0. Or 10 to the minus 1 times x is close to 0. Then you don't know if it's actually x that's close to 0 just because it's small because I multiplied by 10 to the minus 6, right? So depending on how confident I am about whether or not x is close to 0, I could maybe put a lambda squared I here, right? A very large lambda would say I'm very, very confident that x is close to 0. A very small lambda would say, well, it's probably close to 0, but I don't really know. Right? Does everyone see that? So now, this is another least squares problem, right? Could I solve this? What is the setup here? So I have basically my block matrix A lambda I, lambda squared I, is equal to times x is equal to b0, right? If I solve this least squares problem, I get that my x hat is equal to, so it's now, it would be A transpose A inverse. So what is A transpose here? So it's going to be A transpose lambda squared I times A lambda squared I inverse A transpose, so this is A transpose lambda squared I times B. Does everyone see that the solution to this least squares problem is given by this? Yes? So Actually, maybe just for matching everything, I won't put a squared here. I'll just make lambda positive, but put just a lambda here. Doesn't change anything, right? But now when I multiply this out, what is this? This hits this, block matrix multiplication. So I get an A transpose A plus, what's the other term in this matrix multiplication? Lambda squared I squared, but I squared is equal to I, it's the identity. And then this times this, I get an A transpose times B plus lambda I times 0, lambda I times 0, which is, again, the ridge solution. You don't believe me or you're shocked? Like, there's silence, I don't. Okay, does everyone see this? So we have now seen 3 different interpretations of one technique, right? You're looking at it from the condition number perspective. You're looking at it as an optimization problem here. Or you're looking at it from, I like to think of this as ghost data. It's like you're running an experiment and someone secretly comes in and enters some extra data into your experiment. They're trying to help you. This ghost data is also ridge regression. Okay? So this subject is beautiful. Like, it has all these surprise connections and different ways of looking at things. They're just there for you to, like, discover and explore. So please enjoy it. Okay, see you Thursday.